Okay, so here we've got a kind of bio-oriented conservation of energy problem, and it involves some non-conservative forces. So we're going to use our modified version of the energy conservation formula, which is energy initial plus the work done by non-conservative forces. That's going to be equal to energy final. And the example in this case is it's a spring-loaded needle. And so the spring punches the needle in really quickly. I guess that makes a nice clean incision. They give the mass of the needle. They give the spring constant of the spring. They say that it moves 8.1 centimeters before it hits anything that has friction like skin or anything like that. Then they say it moves through skin and experiences this force, and then it goes into an organ and experiences this force. And then they want to know the maximum speed and some other stuff. Okay, so this is basically a very fancy block on a spring problem. Okay, and if you think about a block on a spring, well, this is compressed a distance delta x, okay? And so the spring is going to push it out in this direction, and it's going to get faster and faster and faster and faster until it leaves the spring. So basically this condition, when does it have its maximum speed? You're basically saying that you've taken all of the initial energy, which is the initial potential energy plus the initial kinetic energy, and converting it into pure kinetic energy. I should say final, and I'll include potential energy final here as a term, although we're going to say that this is zero because the spring has uncompressed itself. So that's when maximum speed occurs. So we can say 1/2 kx squared plus 1/2 mv initial squared. So this is zero because it starts at rest, right? This equals 1/2 mv final squared. And so we can conclude from this that the velocity is square root of k over m times x. Okay, that's the maximum velocity. Okay, so that's part A. Really, really straightforward. Okay, so we move on to part B. And in part B, they want the speed at which the flange at the back end of the needle runs into a stop that is set to limit the penetration at 5.9 centimeters. 5.9, that number comes from how far you go into the skin plus how far you go into the organ. So basically what they're saying is how fast is this needle going after it does all this other work. Okay, and so we use the same formula, do the exact same thing. Energy initial plus work done by non-conservative forces equals energy final. For the initial energy, we got choices. We can either say, well, that's the energy that the block or the syringe had when it was still on the spring, or it's the energy it had after it left the spring and it has this speed. It really doesn't matter. I would just as well write 1/2 kx initial squared. Call that the initial energy, right? Now we're going to include all the work that's done by non-conservative forces, right? So there are two non-conservative forces that operate over different distances. So there's this force. So I could say minus 7.6. That operates over 2.4 centimeters, so 0.024. And then there's another force, minus 9.2, times that operates over 0.035. Okay, all of that equals the final energy. Okay, if you punch in the remaining numbers, you get something that looks like this. The only significant thing I really did was for energy final, I said that it's all kinetic. You've done all the work that you're going to do, and so what you're left with is kinetic energy. And if you solve for V, you get 16.1 meters per second. The takeaways from this problem are that, look, this equation just gets used over and over again. Depending upon what you choose to be the starting position and what you choose to be the final position, those are the numbers you'll plug in. In this case, I used the starting energy for both part A and part B. I just chose different finishing locations in each of those cases, but I just mechanically applied the same formula. And this formula will work on all the problems that you have on this problem set.